Welcome back to another session of Econometric Methods course. In this session, we are going to see the decomposition of variance in Y. This decomposition really helps to define two important measures to evaluate the simple linear regression model. One, the coefficient of determination R squared is defined with the help of this decomposition. The other measure is the F ratio. Let us see how the variation in observed Y is decomposed. Let us take a sample regression function. Yi is equal to alpha hat plus beta hat xi plus ei. This sample regression function can be written in the deviation form as well. That is, small yi is equal to beta hat xi plus ei. Squaring both sides, we get yi square is equal to beta hat xi plus ei the whole square. This is a simple a plus b whole square form. So we'll write the square of individual terms and 2 times the multiplication of these two individual terms. So this is the square term of the square of the first term, beta hat xi the whole square plus the square of the second term ei square plus 2 into beta hat xi into ei. So this is the form we get. Yi square is equal to beta hat square xi square plus ei square plus 2 beta hat xi ei. Taking summation both sides, we get sigma yi square is equal to sigma beta hat square xi square plus sigma ei square plus 2 into sigma beta hat xi ei. Now let us take the last term without this 2. We get sigma beta hat xi ei is equal to sigma beta hat xi into yi minus beta hat xi, because ei is equal to yi minus beta hat xi. This is taken from the deviation form of SRF, the sample regression function. Further, it is reduced to sigma beta hat xi yi minus sigma beta hat xi the whole square. Now the beta hat may be taken outside, sigma xi yi minus beta hat square sigma xi square. Now this sigma xi may be written as beta hat sigma xi square, because we know beta hat is equal to sigma xi yi divided by sigma xi square. So this sigma xi yi is beta hat times sigma xi square. So we substitute that value here. Now we get beta hat square xi square minus beta hat square xi square. Both will get cancelled. So this is 0. So the value of sigma beta hat xi ei is equal to 0. So if we substitute in the sigma yi square term, yi square expression, we get sigma yi square is equal to beta hat square sigma xi square plus sigma ei square. We know that yi hat is equal to beta hat xi, or the estimated yi or explained yi. So we may write sigma yi square is equal to sigma yi hat square plus sigma ei square. This may be explained as total sum of squares, or sigma small yi square is equal to explained sum of squares plus the error sum of squares. Coefficient of determination, or R square. We know that sigma yi square is equal to sigma yi hat square plus sigma ei square. Dividing both sides by sigma yi square, we get sigma yi square divided by sigma yi square equal to sigma yi hat square plus sigma ei square divided by sigma yi square. So this will be 1, and the other side sigma yi hat square divided by sigma yi square plus sigma ei square divided by sigma yi square. The first term on the RHS is called coefficient of determination, denoted by r square. So r square is equal to sigma yi hat square divided by sigma yi square. This is otherwise called sigma beta hat square sigma xi square divided by sigma yi square. R square may take value between 0 and 1. If r square is equal to 0, then sigma yi hat is equal to 0. That means model has no explanatory power. If r square is 1, then yi hat square is equal to sigma yi square. That is, the model has full explanatory power. Now let us see how the r square is interpreted. There are 3 possible interpretations of r square in the literature. R square is taken as a measure of goodness of fit. More the r square, more is the goodness of fit. That means if r square is near 1, the model is supposed to be better fit model. If r square is near 0, the fit of the model is bad. So r square is taken as a measure of goodness of fit. Secondly, r square is also explained as r square is equal to explained sum of squares divided by total sum of squares. So it is taken as a measure of proportion of explained sum of squares or proportion of variation explained by the model in total variation of y. So this is another measure. Actually, in fact, r square will be multiplied by 100 to interpret the value in terms of percentage. So if the r square is 0.9, we'll say 90% of the variation in y is explained by the model. If r square is 0.6, we would say 60% of variation is explained by the model. So this is one kind of interpretation given to r square. There is another interpretation to r square. R square we know is explained sum of squares divided by total sum of squares. That is otherwise beta square xi square divided by sigma yi square. So we may substitute beta hat square, that is sigma xi divided by sigma xi square. So we are squaring it, and this is the other term remaining, sigma xi square divided by sigma yi square. Now sigma xi the whole square divided by sigma xi square whole square into sigma xi square divided by sigma yi square. We'll cancel it out. So r square is equal to sigma xi the whole square divided by sigma xi square sigma yi square. So we may now write the denominator as the whole root of sigma xi square into sigma yi square whole square. So we are just taking square root and the square. So it may get cancelled, so you will get the same term. So but still, if you put square here, we'll take the square to the top. That is, we can put square for the both. So it may be written as sigma xi divided by square root of sigma xi square sigma yi square whole square. This term is nothing but correlation measure. Actually, this is the correlation coefficient. So where R is equal to sigma xi xy divided by sigma xi square sigma yi square. So this is the correlation measure, correlation between x and y. So R square is nothing but small r square, or the measure of correlation. So R square may also be taken as the measure of correlation. So more the correlation, more is the relationship between x and y, lesser the correlation, lesser is the relationship between x and y. So R square may also be taken as a measure of correlation. So higher the value, more the relationship between x and y, and lower the value, the lower the relationship between x and y. So here R square is an absolute value. So you will not have minus and negative and positive. So it's a square value, so always it will be positive. So more the value, more the relationship, lesser the value, lesser the relationship. So R square in sum may be interpreted in three ways. One, measure of goodness of fit, the measure of proportion of variation explained by the model, and the measure of correlation between x and y in the simple linear regression model. The Anova in SLRM may be defined with the decomposition terms. Let us see the table. Here we have given sources of variation, sum of squares, degrees of freedom, mean sum of squares, and F ratio defined. We already know there are two components in the total sum of squares, that is exponent sum of squares and residual sum of squares. So the total variation in y is decomposed into the variation due to the residual and the variation due to regression. The exponent sum of squares we already know is defined as sigma ya hat square, that is equal to beta hat square sigma xi square, and the degrees of freedom is defined for this term as k minus 1. K is the number of parameters to be estimated. In this case, alpha and beta are the two parameters that were estimated in this model. So k is equal to 2 here. So 2 minus 1 is 1, is the degrees of freedom for the exponent sum of squares. And so the mean sum of squares we define as beta hat square sigma xi square divided by 1. And we'll see the residual sum of squares, that is defined as sigma ei square. The degrees of freedom for this term is n minus k, where k is equal to 2. And so the mean sum of squares is for this RSS is sigma ei square divided by n minus 2. Now we may define the F ratio. This is the F ratio, the ratio between the mean sum of squares of exponent sum of squares and the mean sum of squares of residual sum of squares, the ratio. So this is the ratio we are getting, sigma hat square xi square divided by 1 and divided by sigma ei square divided by n minus 2. So this F ratio follows F distribution with k minus 1 degrees of freedom, comma n minus k degrees of freedom. So theoretically this ratio follows F distribution with k minus 1 n minus k degrees of freedom. This ratio can be used to test the significance of errors, exponent sum of squares, or the null hypothesis H naught alpha equal to beta equal to 0, that is null model, against the alternative hypothesis H1, that is at least one of alpha or beta not equal to 0. So This F ratio could be used to test the significance of ESS or the significance of this hypothesis alpha equal to beta equal to 0. If the calculated value F star is greater than F k minus 1 comma n minus k, then we will say the ESS is significant, otherwise ESS is insignificant. If ESS is significant, the model is significant and model can be explained further. If ESS is not significant, the model cannot be explained because it is a null model or dump model. Now let us see the relationship between F and R square. F and R square is closely related. F is equal to n minus k divided by k minus 1 into R square by 1 minus R square. So if we know the value of R square, we may find the value of F, or if you know F, we may find the value of R square. For a simple linear regression model, y equal to alpha plus beta x plus u, we defined the estimators of alpha beta and the related measures. Beta hat is equal to sigma small xy divided by sigma small x square. Alpha hat is equal to y bar minus beta hat x bar. Then we defined the unbiased estimator of variance of the stochastic error is sigma hat square, that is equal to sigma e square divided by n minus 2. Using this, we were able to estimate the variance of beta hat, that is equal to sigma hat square divided by sigma small x square. From this, we may define the standard error of beta hat, that is the square root of variance of beta hat. Using these values, we may define the t value for beta hat, that is equal to beta hat divided by standard error of beta hat, that follows t distribution with n minus 2 degrees of freedom, and for the large sample it follows the standard normal distribution. We have to remember here that this is the t defined for the significance of beta, that is beta is taken as 0 here. So this ratio will be used as the t test for testing the significance of beta equal to 0. And similarly, the variance of alpha hat we already defined in terms of variance of beta hat, that is variance of alpha hat is equal to variance of beta hat into sigma capital x square divided by n. Then that leads to standard error of alpha hat, that is nothing but square root of variance of alpha hat. Again, the significance of alpha hat, alpha can be tested using this test t statistic, t alpha hat is equal to alpha hat divided by standard error of alpha hat. This follows the t distribution with n minus 2 degrees of freedom. And also we defined R square in our previous explanation. R square is equal to beta hat square sigma small x square divided by sigma small y square. This is a measure of the goodness of fit or the proportion of variation explained by the model or the correlation measure. The F ratio is defined as beta hat square sigma xi square divided by the degrees of freedom 1 divided by sigma ei square divided by n minus 2. This F follows the theoretical F distribution with 1 degrees of freedom and n minus 2 degrees of freedom. So this is the F ratio defined. This F ratio can be used to test the significance, overall significance of the SLRM. So the null hypothesis for this F test is alpha and beta are 0 jointly. So we are trying to test the significance, overall significance of the SLRM using this ratio. Now these defined values may be put in a template reporting form. The SLRM results are reported in this template. Y hat is equal to alpha hat plus beta hat x. The standard errors are given below like this. Within the arc bracket, the standard error of alpha hat is given, and in the square bracket, t value of alpha hat is given. The beta hat and the standard of beta hat and t of beta hat is given below the value of beta hat. In the side, we'll usually give R square value and F value, F ratio value. So using this template, we will interpret the SLRM. The order of interpretation is as follows. First, the overall significance of F is evaluated. If the F star is significantly different from the critical value, then we will say the model is significant, otherwise the model is insignificant. Then we will interpret the R square measure for the total variation explained by the model. Then we will evaluate the individual regression coefficients. In fact, in the usual SLRM, alpha hat will not give much meaning. Mostly the beta hat is the value that will be interpreted quite often, because the beta hat will have the meaning, and theoretical interpretation could be possible for beta hat. And so thirdly, we will evaluate the significance of beta hat. If the calculated beta hat is significantly higher than the theoretical table value, then we will say beta hat is significant. And lastly, if the beta hat is found significant, we will interpret the value of beta hat. There is a marginal interpretation of the meaning of beta hat. That is, beta hat is the measure of variation in y with respect to a unit change in x. So beta hat is a measure of variation in y with respect to a unit change in x. In today's class, I summarized many of the statistical measures that were defined on the SLRM and the measures that are used to evaluate the overall significance of the regression model and the individual significance of the regression parameters. And these statistical measures are used for the econometric purposes. The application of these measures will be seen in the next classes. Thank you.